First speaker is Matt Brecknell from Kry10. And yeah, he will talk to us about dynamic seL4-based systems and how to design them for verification.
Cool. Thank you, Gerwin. I'm Matt Brecknell. I lead formal verification at Kry10. I previously worked on the seL4 proofs with trustworthy systems. Now, you might think that means that I'm currently up to my eyeballs in proofs, but actually, I've been spending a lot of my time thinking about system design. Of course, we do want systems with verified properties, but before we can have that, we need a design that can support the verification of those properties. So we've been building an operating system at Kry10 for a couple of years now. So we clearly have a design. It's a multi-server operating system based on seL4, and seL4 gives us strong isolation between these components, and we can use that to build resilient systems that are secure, reliable, and robust. We also have an admin server, which can talk to a remote management service in the cloud, and that allows operators to perform various functions on the device. In particular, they can deliver software and configuration updates and have those applied to the system without rebooting, without interrupting service. So that gives us manageability. But it doesn't mean we have a very dynamic OS. And that raises the question, well, how do we get confidence that we always have the system in the configuration we want and that we have the appropriate level of isolation? We know how to get that for static systems, but we're still figuring out how to do that for dynamic systems. And so what's missing from this picture is a small core component that we can formally verify and that tells us that we have those properties. So I'm going to start with a little story. And this will give us some idea of the kinds of dynamic features that we want to support, but not necessarily the way that we want to support them. So we're going to imagine that we're a sort of medium-sized engineering company. We have an office in the city. We have a remote location out in the field. We want to set up some kind of industrial process there and have it automated and unattended. So we're going to need to build a device. We haven't heard of Kry10. We haven't heard of the microkit. We've somehow come across Nick's Rust framework, so we're going to build this from scratch. And here's the first version of our device. We have some sensors, some actuators, and a control system, which sends commands to the actuators based on what it reads from the sensors. We have a logger that receives trace data from the controller and sends it out the network through a satellite dish. We also have an updater component, which can receive new system images from the network, write them to flash storage, and then trigger a system reset through a watchdog device. And that gives us a kind of a crude mechanism for updating the software on the device. The updater also has to tell the controller to shut down the machinery, because even though reboot only takes a few seconds, that's a bit longer than we want to leave the machinery unsupervised. Okay, so we ship it out to site. Seems to be working, but when we get back to the office and look at the data, we can see that the process isn't running as efficiently as we would like. But unfortunately, the data we're getting back isn't enough to tell us why. And for some reason, we can't replicate this in the lab, so we're going to have to debug it in the field. The way we're going to do that is by sending out new versions of the controller to send back more data. So we do that. We have to reboot and shut down the machinery. We still don't have enough to figure out what's going on. So we have to iterate, and pretty soon we get a phone call from the executives asking us what's going on. We try to explain, but they tell us to find another way. So we build a second version of our device. And this one, the updater works a bit differently. When it wants to ship a new version of the controller, it just loads it into the running system beside the existing controller. Now this new controller is reading the sensors, but it's not actually producing any actuator commands yet. So that gives it a while to warm up. The next thing that happens is the updater reaches into the C space and V space of various components and rewires the actuator signal from the first controller into the second. The second one just passes that straight through to the actuators. But this gives the V2 a chance to synchronize, and when it's ready, it can take over the actuators. And then it can tell the updater it doesn't need the V1 anymore, and the updater gets rid of it. So that allows us to seamlessly update the controller on the system and ship new software, figure out what's going on, and eventually fix the problem. So the good news is we managed to do that, and we now have a working system running really sweet. But the problem is we've now got a fairly complicated system. And maybe that's a problem. In particular, the updater now has a lot of power in the system. It has complete control over the controllers, because it has to create and destroy them. And it has quite a lot of control over the actuators and sensors, because it needs to reach into their C spaces and V spaces to rewire connections. So if it has a lot of power, then if there's a bug in the updater, that could have fairly serious consequences for the system. But it's also doing some fairly complicated stuff. So that means there's a fairly high likelihood that it has some bugs. Of course, likelihood and consequence together spell risk. And to make it worse, the updater is connected to the network. So maybe this isn't quite the right approach for this situation, but it was kind of cool what we did there. So maybe the actual problem is that this is a single-use design. We built this just to solve a single process optimization problem. So if the problem is that, so that means that it's not really worth investing in the correctness of this component. But if the problem is that this is too specific, maybe the solution is to generalize and build something that works not just for this system, but for all the dynamic systems that we want to build. So if we're going to generalize, we first need to pin down the kinds of dynamic behaviors that we want to support. First thing is we want to be able to add and remove components to a running system without interrupting the ones that are already there. So we should be able to add a component, the first two keep running. Similarly, we should be able to remove one. And finally, we should be able to redeploy resources when we add and remove components. So we're not just putting new stuff into fixed boundaries, but we can actually redraw the boundaries. Now, secondly, if components are usually connected to each other, and so if we're adding and removing components, then we also need to add and remove connections. So if we have some existing components and we add a new one, it wants to connect to an existing component. That means we need to add that connection to a running component without interrupting that component. We also need to be able to remove connections from running components. Now, if components don't know ahead of time how many connections they will have, they also don't know how many resources they need to service those connections. And so when a client connects to a server, we usually want the client to provide the resources to the server that the server will use to serve that client. When we disconnect, we better get the resources back. And finally, if we're adding and removing connections and resources to components while they're running, we'll need to coordinate with those components. So here's what I think the generalized update pattern looks like at a very high level. Hardware is controlled by seL4. In user space, there's a single trusted and privileged component called the root server, and it runs forever. The root server can create and destroy other components, so they're ephemeral. As far as the root server is concerned, they are all untrusted and unprivileged. And so the root server works to ensure that they remain isolated from each other, mostly. They are allowed to have endpoints, notifications, and frames shared between them, but they can't grant capabilities, and they otherwise only have access to their own resources. And from the security theorems, that tells us that they can't do anything to redeploy resources in the system. But they can make requests to the root server, and maybe the root server will do something on their behalf. So that means that the root server completely mediates all of the dynamic behaviors in the system, which means it maintains oversight, so complete knowledge and complete control over all of the state in the system that is relevant to security. So if we want to understand the dynamic behaviors of the system, we just need to understand the root server. So the first design insight then is that we should be able to specify the dynamic behaviors as configuration, because then we only need to understand the configuration. So we need some sort of configuration language with various attributes. We'll need some low-level abstractions, essentially inheriting those from seL4. And that means we can define a wide range of systems efficiently. We want some high-level abstractions that allow system designers to work at the level that they're used to. And we want some abstraction mechanisms to bridge the gap between them. We'll give the language a formal semantics. That means we can reason about dynamic systems at an appropriate level of abstraction. And we'll provide libraries and base configurations to give a secure configuration out of the box, and maybe some tools to help system developers easily make sensible configurations. Okay, some advantages of this approach means we get a separation of concerns between systems development and verification. So verification works from the configuration language down. We want to verify that the root server enforces the semantics of the configuration language on the system. That's a big job. But we only have to do it once. The reason for that is that the configuration language allows developing a wide range of systems over the lifetime of our platform, while the root server stays quite stable. And then reasoning about all of those systems we can do in terms of the configuration and not in terms of still the low-level abstractions of seL4. And that way we get some reuse of the assurance argument. Now, as the system evolves, so will the configuration. So it's also useful to think about the configuration as an object capability model. Now, seL4 also implements an object capability model, but it only has low-level abstractions. So we want to add some high-level abstractions and some abstraction mechanisms to our model. So let's look at what those are. So the two high-level abstractions I want to add, and these are fairly standard, protection domains and leases. A protection domain just identifies components in the system at runtime. For static systems, we usually only need to identify them at build time, but at runtime, we want to keep track of which resources belong to which components at runtime. And then the root server can enforce rules about those resources. For example, if we want to configure a TCB with a C space, then they better belong to the same domain. And that way, the root server can still enforce separation even though the system evolves at runtime. But those rules are a bit too strict, and if we just have those rules, components will never be able to talk to each other. So we need a loophole, and that's what leases are for. At least temporarily assign some resources from one domain to another. We call those the lessor and the lessee. We can have subleases. So if you lend me some resources, I can lend some of those to somebody else. We can terminate leases to get resources back, and either party can initiate the termination. But we need to coordinate this so we don't get any unexpected revocations. Now, if the lessee terminates, then we can assume they've already stopped using the resources, so we can just revoke them and then notify the lessor that it has its resources back. But if the lessor terminates, then we need to give the lessee a chance to stop using the resources. Otherwise, it would get an unexpected revocation, which could put it in a bad state. So we notify the lessee and wait for them to acknowledge. And then when they do acknowledge, we can revoke the resources and notify the lessor that it has its resources back. If the lessee doesn't acknowledge, then we time out. And the root takes some kind of action on the lessee, which is configurable. So that might be nothing, or it might be we kill the lessee and restart it. Once that's done, we revoke and notify as before. So we have two kinds of leases. For endpoints, notifications, and frames, these are what we use to communicate between components. And so those are shared leases that allows the lessee and the lessor to communicate. But when we're leasing untyped memory, we require sort of exclusive use, so the lessor loses the ability to use that untyped memory while the lease is active. Leases also follow some rules. For example, the root server must have exclusive control over the original cap to the resource, otherwise the lessor could bypass the termination protocol. Okay, so those are the two high-level abstractions. Again, they're fairly standard, and similar things appear in lots of other dynamic capability-based operating systems. But then by themselves, they're not quite enough. Remember, we want to be able to express the allowable dynamic behaviors as configuration. So we can't do that with protection domains and leases alone. So what we want to do is then enrich the model with some abstractions, mechanisms, and effectively make the root server an interpreter for an object capability language. So the two mechanisms I want to add are scripts and methods. A script is a binary encoded executable function that operates on the root server's object model. And a method is just a script that's already bound to some capabilities. Let's have a closer look. So once again, a script is a binary encoded executable function that operates on the root server's object model. It'll have a header that describes its parameters and return values, and then a sequence of instructions. So it's like a high-level assembly language, or a high-level machine code that operates on a high-level machine. Its instruction set will contain operations on the root server object model, so on leases and frames, signals, methods, and so on. And maybe when we want to create stuff, we'll embed like a declarative language for doing that that'll be a bit like CapDL. I'm not quite sure about that yet. We'll have the usual things for computation and control flow, and we'll have some cryptographic primitives because we want to authenticate remote commands and then attest to their results. And we want to do that in a secure context, in a trusted context. Okay, so then a method is a script that's already packaged up with some root server capabilities. And so when we run that method, the script will use the capabilities that it's bound to. And the important thing is that we can't open the package. So we have a capability to a method, we can run it, but we can't get its bound capabilities out. And that allows us to build new abstractions. So we can talk about connections, and opening and closing them. We can talk about app packages and loading them, and what that means. And now we can give methods to untrusted code. In fact, that's the only API that we give to untrusted code. And that gives us very fine control over the dynamic behaviors in the system, including those that can be triggered by untrusted code. Okay, so I said before that we have this dual view of this model. We can either see it as an object capability model, or we can see it as configuration. And so far, I've mostly been taking the object capability model view. Let's try to take a configuration viewpoint and think about what it means to describe a system. Of course, the methods are quite powerful, so we can do this in many ways. So this is just one simple approach to it. We can describe an app package essentially as a constructor script. It's a script that you execute to load the app and get it running. Take some parameters for its, the protection domain capability that it gets loaded into, and some initial leased resources. And we also package it up with the sort of binary representation that will then get fed into those parameters when the app is loaded. And then a system is really just a collection of app packages together with a specification of which components get connected when the system loads. Okay, to finish off, I just want to step through an example of using a method to set up a connection between two components. We have an untrusted code for a sender and also an untrusted receiver component. The idea is we want to set up what we call a software-defined data diode, so we can send data from the sender to the receiver, but the receiver has no way to send data back. Initially, there's no connection at all, but the sender has a request method that it can use to call a service method on the receiver. But all of this is inside the root server. So this connection here will have been created by the system loader script. Okay, so to start opening the connection, the sender calls its own request method. And the first thing that does is it will create a send buffer out of its untyped. And it will map that into the sender's address space. It then creates a lease for that send buffer and passes it to the service method for the receiver. So now the service method has a reference to the lease. Service method accepts that lease and gets a reference to the send buffer, which then maps into the receiver's address space, but read only. The service method then creates a lease on the receiver's notification and returns that to the request method. So now the request method has a reference to the lease to the notification. It accepts that lease and gets a reference to the notification, but that's a send-only reference. It then maps that into the sender's capability space. If we get rid of the temporary references, we can see what's left behind. And inside the root server, we have the request method has references to leases, so it can terminate those if it wants to. We also have the sender can signal the notification, can write to the send buffer. The receiver can only receive on the notification and read from the send buffer. So the receiver has no way to send data back to either the root server or the sender. Now, if you're paying attention, you would have noticed that the receiver never got a chance to interact with anything. All of the receiver's side of the connection setup happened inside the root server. So it's never had a chance to leak any of its secrets. But that's not even the punchline. The punchline is that even though we set this connection up dynamically, we can analyze the state of the root server to see that this is the only access that the receiver can ever get. And that's why I want methods in my object model. Okay, quick note on status. This is all vaporware. I'm still working on the design concepts, and there are lots of details still to work out. Yeah, it turns out bookkeeping and deletion are hard. Once that's done, we'll build some experiments with some example systems just to make sure we have the right design. Then we can start formalizing the object capability model and hopefully make some tools to make it easy for system designers to build sensible configurations easily. And eventually we'll give those to customers. Longer term, we'll be building verification frameworks so we can actually prove the functional correctness of the root server. Okay, so to summarize, we have a problem. So we want to build very dynamic systems. We want to verify that they always meet our security and design goals, even after a sequence of updates. But we don't want to slow down as systems developers. So how do we do that? And I think the solution is to enrich our capability model with abstraction mechanisms, including methods. That's it.
Thank you very much. Questions, please.
the big graph.
Mhm.
So here you had like the lease on the left, and it created the send buffer out of the untype.
Yep.
That made good sense, but then you already had this notification on the right, yeah?
Yep.
And then you created a lease to the existing capability. Is that how to say that?
Yes.
Okay, so I was just curious about how that worked. It seemed like you already had to have the capability for that lease, but then so the lease.
Well, I mean, these methods can do pretty much anything to the object model.
Okay.
So they can if the service method already has a reference to the notification, it can create a new lease to share that out with a new badge. In this case, it has a reference to some untyped, so it can create a buffer out of that untyped.
Okay, I see.
Yeah.
Yeah, I think my confusion was it made a lease out of its own capability, and it seems like it made a lease out of this other object's capability, or is it?
So this lease is created by the service method, which kind of is associated with the receiver. This one is associated with the sender.
Okay, thank you.
Yeah, so this is an inspiring and ambitious plan.
Yep.
I had a question which you answered, I think, almost the last slide, which was how much is plan and how much is current work.
Yep.
But the other question is, this looks like a very generic framework that could be useful to a lot of people. So
Mhm.
are you planning to do that mainly for Kry10 internal or open sources to the community?
Excellent question. I don't know. I think it depends. We're currently looking for funding for at least parts of this work because there is a lot of it and we want to accelerate that. If we can get funding from public sources, then that would encourage an open source model. If we get funding from private sources, then we'll have to do whatever maximizes their return, which might still be open source, but yeah, we'll see.
Okay, one last question.
Hi, one of the things that the Debian project has talked about doing for 25 years is moving less away from system configuration in terms of driving things with triggers and scripts and more in terms of a declarative language.
Mhm.
And it seemed like a declarative language for this type of system configuration is something that, well, I can't say for you if it came immediately to mind, but it doesn't seem to be the easiest solution or your first resort. Can you elaborate on why not? Well, let me add. One of my assumptions is that a declarative system is easier to prove theorems about, and maybe that's not true.
Yeah, I don't know. I think we want the option of doing things the imperative way because we don't want to close any doors on ourselves, and it's very easy to close doors when you make something declarative. But yes, I think you're right. It would be great to have at least a declarative kind of subset of the language that makes things clearer and easier to verify things about.
Okay, because the hazard that you run into with, say, Linux distributions running these scripts is that they're fully general shell scripts, which
Yep.
means you really have no assurance at all. I mean, the shell language itself isn't even formally decidable. I don't think we'll let things get that bad here, but it strikes me as a hazard.
Yeah, and certainly, I mean, I want to make it fairly general, but that means that, yeah, there will be configurations that don't make sense, and there will be configurations that do. And so when you do make a configuration, you'll have to do some work to convince yourself that it's a sensible one. But yeah, we're going to provide tools to help with that.
Okay, let's thank Matt again.